We are Rover Manipal, an interdisciplinary team of 37 undergraduate students, and we are proud to present our rover for the International Rover Challenge 2026. The rover's electronics are built around a custom PCB stack designed for modularity and reliability, consisting of 3 boards. A power distribution board, which features fuses and specialized ICs to safeguard against reverse polarity and overvoltage. The MD board, which houses the motor drivers, features a design which isolates high current lines from sensitive signal traces, and the motherboard, hosting the ESP32 controller board and LEDs for quick signal state verification. The rover uses metal 52 AC transceivers with 9 dBi antenna for communication, but can switch to the 868 MHz LoRa module as a backup. To test the rover's communication system, it's driven up to 2 km in line of sight, evaluating the metal 52 AC's range, after which the transition to the LoRa module is tested. The rover is also equipped with an easily accessible kill switch that allows for the immediate shutdown of power in the event of an emergency.
For the instrument deployment and maintenance operation, we have developed a 6DF robotic manipulator based on the 4-bar mechanism, actuated by custom cyclotron gearboxes of reduction 50:1, with a reach of 1.3 meters. The modular end effector features a new dual-action paddle gripper that uses a twin lead screw design, which is coupled to a custom bevel differential to achieve pitch and roll. We have redesigned our GUI to display feeds from analog cameras alongside delta-encoded strings that are used to control the rover and toggle between inverse kinematics and forward kinematics. For testing the robotic manipulator, we perform a series of tasks including picking and placing objects weighing up to 7 kg, flipping switches, turning knobs, and controlling a joystick.
For the reconnaissance and autonomous delivery operation, our rover utilizes a custom 5-bar suspension that is kinematically constrained through mechanical stops. Reconfigurable torsion springs are used to stabilize the rover over irregular terrain. The readings from the onboard IMU provide the PID controller with feedback for hill assist. A tubular space frame chassis with modular front and rear sections has been designed and manufactured in-house to mount the robotic manipulator and science module. A full float bearing assembly minimizes load transfer to the motor shaft. We have designed a new 3D printed wheel using PLA barrels and TPU tires. The rover is made to traverse through different terrains to test the suspension and wheels. FEA simulations are conducted to ensure the structural stability of the chassis.
For autonomous delivery, the robotic manipulator uses MoveIt 2. It handles motion planning, inverse kinematics, and collision checking to help with the picking and placing of objects. For autonomous traversal, NAP2 uses occupancy grids from RTAB map to generate global and local cost maps. Global path is computed by the SMAC planner, while the DWB controller adjusts velocity to avoid local obstacles. Colored markers are located using a custom search pattern and are detected using OpenCV. Once a marker is detected, a parabolic controller adjusts the rover's speed and direction based on the marker's position. We use Gazebo to simulate terrains and test the navigation stack before deployment.
For the astrobiology expedition, we have designed a science module comprising of a chemical turret to conduct in situ soil analysis, detecting labile carbon, proteins, carbonates, and nucleic acids to assess the scope of life. We use bromothermal blue for accurate pH testing and to avoid cross-contamination caused by sensors. The module includes an auger mechanism that can collect a 10-gram soil sample from below 10 centimeters, seal it in a cache container, and then drop it at the desired location. A clamp bucket is used to deposit soil into a turret driven by a Geneva wheel. We have 2 sensor modules, HAN and Leia, which assess atmospheric and lithological conditions. Onboard cameras aid in site selection with captured images stitched into a panorama complete with all necessary parameters. Sensors are tested in various conditions to ensure accurate readings. Different materials like PLA, ASA, and steel have been tested for the auger, with steel proving to be the lightest and the most efficient at soil collection.
The rover's development follows agile principles to ensure smooth and efficient work. Development is managed using Kanban cards and Gantt charts on superthreads. The team maintains an active social media presence to promote our project and to encourage student participation. We organize open houses and expos. Additionally, we participate in technical fest and exhibitions to demonstrate our rover's capabilities and attract potential sponsors.